my name is Vitaly Libayev, and today I will present you our work conducted at JetBrains, where we leverage anonymous logs to improve code completion system in IntelliJ-based IDEs. That approach is used by default in the most IDEs and languages for now. So let's start with general problem statement. We know from previous research that using artificially generated data for training a model leads to worse performance in the real world. However, it's impossible to collect a lot of realistic data due to various privacy laws such as GDPR. And this regulation impacts software development tools, including IDEs, so they can collect only anonymized logs. However, can we really use these logs in their anonymized form to train models to improve something? In this paper, we argue that the answer is solid yes, and we're going to demonstrate on example of code completion how we improved that in last couple of years using these anonymous logs. So the talk is structured as follows. First, we provide a brief overview of code completion. Then we'll describe approach, what features we use, what logs looks like, and what models we train. Then we share the numbers about evaluation, both offline and online, and then we make a conclusion. So let's start with how typically code completion ranking works. Usually code completion starts with phase of generating all possible proposals which can be used in particular location. These proposals are taken from static analysis, and there might be up to several thousand of such proposals depending on location. Since there might be many of them, we need a proper ranking procedure to ensure that the most relevant ones show in the very top. So historically, this ranking might with heuristics, but there are several problems with them. The heuristics based on many assumptions that might be wrong, at least in some particular cases. Then, over time, maintaining these heuristics become more and more difficult, and integrating new ones is also difficult because you need to keep in mind that there are others that may contradict with new one. Also, these heuristics tied to a particular language, and it's pretty hard to ensure that they will work in different languages. Therefore, we propose a solution to replace this heuristic with machine learning as final ranking step just before showing the items to the users. So, let's overview the general pipeline of our approach. As we explained, the process is divided into two places, the user machine and the remote server. Firstly, we calculate a set of anonymized features that don't contain code itself nor any private information, but describe where code completion is triggered and describe the show elements. Then we collect these features as logs, that format kind of similar to JSONs. Having them as data, we can train the necessary machine learning model to rank the candidates and evaluate it offline, and once we check that everything works properly, we can deploy it into IDE for future users. Since users get these models, they can start working and we can collect logs again. Then once we have these logs, we can evaluate model performance. As you can see, collecting logs here serves two purposes in this pipeline. First one is collecting logs for training, second one is for evaluating. Therefore, we can do both at the same time. So this can be used as a cycle to improve. We can evaluate previous model and train a new model exactly at the same time. So let's take a simplified version of how these logs look like. We can see that user here started sessions, then typed 2 additional characters, went down one time in the selection, and finally selected the token. This is how IDE could look like just before the selection. And here is extended structure of the logs. For each event, we store the general features like query length and whether completion triggered in static context. Here it's static because mine is marked as static. And then it contains also a list of suggestions with suggestion-specific features like its length, parameter counts, and kind like method or field. And finally, we transform this data into tabular form. As an example, we use completion sessions that ended in a certain success. The user either explicitly selected the suggestion or typed it manually. Either way, the correct suggestions obtain a positive label and all other obtain negative. So, and we can train a model on these labels by these features and try to predict whether a particular item is going to be selected or not. So, since the model has to work in production, it must adhere to quite strict limitations. First, it has to be lightweight, no more than a couple of megabytes, because it's important to keep the distribution not that big. Crucially, the inference must take no longer than 10 milliseconds, since it works after traditional ranking and updating the items order should happen seamlessly. And finally, the model has to be integrated into JVM because all IDEs work on JVM. Because all of that, we decide to use CatBoost models because they suit all of these things. So once we have a model, we need to evaluate it. We collected some data from users of EIP programs for 2 weeks. First week we use just for training and tuning hyperparameters, and second week we use for testing. Having this data, we trained model and computed several metrics. In this evaluation, we compared metrics recall at k. It means probability of having relevant item at top k positions, and we also evaluated only initial lookups. That's ordered items which were shown very initially to the user, and we think that this affect future user behavior the most. And we see that the most noticeable improvement in metric recall at top 1 in initial lookups. That sounds good, but we still need to check how would it affect user behavior. Therefore, we need to perform online evaluation. Here is the second stage of evaluating model. We use this in form of A/B experiment. We split some of users during early access program into 2 groups with several hundred users, and then calculated several metrics for both of them and compare. So we notice that some of this metric has significant statistical significance, others don't, but p-value is still quite small. For example, a ratio of explicit selects, the cases when user decide to choose element explicitly by pressing enter key or tab key, increased 5%. Other metric also increased in a good way. For example, a ratio of type select when user decide to type the entire token manually is reduced for 6%. And some other metrics also improved, like ratio of sessions when user decide to start completion session manually by shortcut is increased and with statistical significance. So also we checked that it doesn't make performance that bad. It's also only increase time before showing the lookup for 20 milliseconds. That feels okay. So to conclude, we presented approach to using anonymous logs to train machine learning models for ranking completion suggestions. We evaluated in offline and online using A/B tests, and it shows result better than defaults. And as a result, we described the approach that we used to improve completion in many languages, and it's now used by default. So, thank you for your attention. Here are some QR codes for the paper and JetBrains Research Laboratory. And if you have any questions, feel free to write me to the email on the slide. So, thank you.